Hello everyone. Welcome to your Math 275 Differential Equations Exam 2 review. My name is Vedang and I'm an executive tutor at the Engineering Tutoring Centers where we spearhead large-scale math operations for everyone. I have with me Arnav and I'm going to let him introduce to yourself shortly. Well, welcome everyone. We've recently rebranded as Pulse from Engineering Tutoring Centers and we'll go into that shortly as well. Before we get started into this review, I wanted to give you guys a heads up as to where you can find this. And so this link above, which is math.asu.edu/mat275, if you click on exam to review and its practice problems, you can access the same questions that our tutors will be doing. And before also, prior to getting and jumping into the questions, over the few years that I've taught 275 and when I've taken it myself, I've noticed four things that really stood out to me before approaching every Math 275 problem. And let's go through them. And, the first one being read the problem slowly and circle the givens and what you're asked to find. I've seen many students underline the values, circle the givens. I myself rewrite the givens again so that I don't miss out on anything, or, if there's a certain given that I'm missing out or an initial condition that I didn't take note of, it helps me when I rewrite the givens. Number two being defining my variables and writing the function or equation that models the situation accurately. For example, including the domain and any units if they're important, knowing the inequalities for a linear ODE, right? That's important that you know that. Number three, and I cannot emphasize on this enough, is that your calculator must be a friend and not your enemy. I've seen countless times where students know how to work out the question and solve the question, but then they set it up in their calculator and input it incorrectly, which in turn gives them a wrong answer. And I keep telling everyone this every time you're practicing, every time you're doing an exam and, a practice exam, or even when you're solving practice problems on Edfinity or whatsoever it may be, please use the same calculator, because students tend to set up their calculators in an intuitive way, which will help them during the exam. You know, you don't need to figure out the new controls, the new keys, because you're already familiar with your original calculator. And so once again, your calculator must be a friend and not your enemy. Number four, being that interpret your answer in context. Check the units, state your conclusions, see if the value is reasonable, make your assumptions. For example, if you're doing a Laplace and you know there's no way of factorizing or getting a partial fraction decomposition method done, check it out again, go through it again. Once again, see if the value is reasonable. You can find us at ECG 152, and yeah, it's called the Pulse Hearing Center, and we can't wait to see you in person. I will now hand it over to Arnav, who's going to go through all questions with you guys. So good luck and have a good day. Thank you.
Okay, thank you, Vedant, so much for covering what FSC tutoring is and where to find this review for differential equations. So, hello everyone. I'm Arnav. I'm a tutor. I work at the engineering tutoring centers, and you can find me in ECG 152. So, today we will be going over the review for differential equations for exam 2. So, yeah, this is pretty interesting stuff. You'll be using it a lot ahead as well. So yeah, I'll directly just start with section one, question one. So this question here, it's asking us to determine what the longest interval is for the given initial value problem, right? And there's the differential equation given to us, which is okay. So let me start with question 1A. Oh, so it's question 1A. And this one is t multiplied by t minus 4 multiplied by y double prime is equal to plus 3t y prime plus 4y, and this is equal to 2. And the value for t naught given to us is 6, and there are some initial conditions given to us. Sorry, y prime of 6, -1. Okay. So as we know, like the standard equation for um a yeah, the standard equation, the second order standard form for a differential equation looks something like a of t y double prime plus b of t y prime plus c of t y, and that's equal to some function in terms of t, right? And yeah, so our goal is just to convert this equation into something like this. Obviously, this equation that's given to us in the question is not in its standard form, right? So we have to convert this into our standard form, which we can find when we divide this whole equation. Oops. Yeah, when we divide this whole equation by divide equation by t multiplied by t minus 4. So we want to isolate the y double prime equation, like variable, right? So we do that by dividing the whole equation by t multiplied by t minus 4. So what we get is y double prime plus 3t y prime, and this is divided by t minus 4 plus 4y t minus 4 equals 2t, oh, t minus 4. Okay. So we like there are points at which this equation could fail, right? So if anything divided by 0, any number divided by 0, 1 divided by 0, that's undefined, right? We cannot have this. So in order to avoid this, we have to know what points are like what points will cause this, right? So we do not want the denominator to be 0. So for that to happen, we know what points the denominator will be 0 at, right? So that is t minus 4 cannot be equal to 0, and that happens at points where t is equal to 0 and t equals 4 plus 4 to be precise, right? So these are the points at which the equation fails, right? These are like problematic points. So the already like t0 given to us is at 6, right? So anyways, we know like 6 doesn't lie between 0 and 4, since it's plus 6, right? It doesn't lie between 0 and 4. It is 6 is to the right of both these points, right? So our interval for the largest interval, which contains 6, is from 4 to infinity. So I'll just write largest interval interval is yeah, 4 to infinity. Yeah, so pay attention at these brackets because these are round brackets, right? What do round brackets mean? Round brackets mean that we're getting very close to the value, but exactly not reaching it. Because if we plug in 4 instead of t naught, our equation fails, right? We do not want that to happen. So we'll move ahead with part B, question B. And this says that it's t plus 1 y double prime plus t multiplied by y prime plus y equals sec of t, right? And like there are some initial values given to us for the equation, that's 2, and y naught of 0 is -1. So that's that, right? Again, we want to convert this into a standard form so that we have an isolated y double prime and we can find the problematic points, right? So if we go through this again, is we will be dividing equation by t plus 1. in order to isolate y double prime. So t plus 1. Okay, so we have y double prime plus t divided by t multiplied by y prime divided by t plus 1 plus y divided by t plus 1 and sec of t divided by t plus 1. So one thing if you'll notice is we have a sec, like that's a trigonometric function, right? Sec, and sec has some values where it's undefined as well, and we cannot have undefined in the solution, like anywhere in the differential equation given to us, the second order differential equation given to us. So we will also have to account for the problematic points where sec of t is undefined, right? So problems occur at what points? So I'm just gonna say, so these are our problematic points, and these occur at t plus 1 equals 0. We do not want that to happen, right? So one of the points is t negative 1, and the other point is where sec of t uh, sec of t is 0, and that happens at, so since sec is, I'm just gonna make a small rough column over here. So since we know, like, second is the inverse of cosine, and cosine is 0 at pi by 2, values increasing with uh, pi. So sec cannot be those values, because if it's those values, it'll be undefined, right? We do not want our second to be undefined. So the values for this is, it gives out a pi by 2, because sec at pi by 2 is undefined, and any value like increasing with pi by 2, right? We do not want these values. Sh- and the t naught given to us is 0, right? And we have to find the largest interval where, yeah, so we have to find the largest interval in which the given initial value problem is to have a unique twice differentiable solution, right? So okay, so what we know is t0 at 0 lies between negative 1, because negative 1 is to the negative 1 is to the left of 0, right? And pi over 2, which is approximately 1.57, is to the right of 0. We cannot have that happening, right? Pi over 2. So our largest interval where this, so our largest interval where this given initial value problem is to have like unique twice differentiable solution is between negative 1 and pi over 2. Well, is negative 1 and pi over 2. Okay, so that's it for this one, and we'll move on to the next solution, right? So it's given to us, suppose y1 of t is equal to t and y2 of t is t squared. And these are both solutions of the second order linear equation y double prime plus p of t y multiplied by y prime plus q of t is 0. And this is basically a multiple choice question which asks us which of these functions below are guaranteed to also be solutions of the same equation, right? So first we have to find that happening. But the homogeneous, okay, so the homogeneous equation given to us is y double prime plus p of t, y prime plus q of t. Oh, that's plus q of t is 0, right? And so for any homogeneous linear differential equation, so any linear combination of the solution will also be the solution to the given differential equation, right? So y1 of t is t, and okay. So we'll have constants multiply y1 of t plus c2 y2 of t, right? So this is guaranteed to be a solution. So c1 t plus c2 t squared as well, right? So let's run through the options so that we can know which one is a definite solution of this, is a guaranteed solution of the same equation or not, right? So let's run through y at option A, which says that y is t squared minus 1, right? So this requires a constant term -1, but constants are not in the span of t and t squared, right? So this is not guaranteed. So we can just remove this out of any of our possible solutions. B states that y equals phi t, right? So if we, I'm sorry, excuse me. So if we plug this in, mm, so y, so 5t plus 0 multiplied by t squared, right? So it is a linear combination of the two solutions. So this is guaranteed, right? So B is guaranteed. So this is one of the options. Let's run through C. And C says here that y equals -9t squared plus 17t. So if we plug this in and we go again, so this would be 17t minus so this would be in the, okay, so this matches up with the equation we have here as well, right? So this is also guaranteed to be a solution of the same equation. And if we run through D says that y equals 0, right? So the zero function is always a solution of a homogeneous linear equation, so this is always guaranteed. So our final options are B, C, and D. So this wasn't too tough, right? So, okay, let's run through the next question, where this one says that find a real valued solution to the following initial value problems. And the equation given to us is y double prime minus 6y prime plus 13y equals 0, with y0 equals 1 and y prime of 0 equals 1 as well. Right, so the standard method is we solve the characteristic equation, then we write the general real valued solution, and then we use the initial conditions to find the constants, right? So basically, if we want to find the characteristic equation, what I'm going to do is I'm just going to substitute y double prime and y prime and y in terms like for a different variable. So I'll say like y double prime is r squared and y prime is r, and y is just it's just going to be nothing. So it's going to be r squared minus 6r plus 13 equals 0. So we have a quadratic equation here, right? And if we use the quadratic formula, which is negative b I'm just going to write the quadratic. So it's negative b plus minus square root of b square minus 4ac divided by 2a. And if we plug this in over here is our like unique solutions for the quadratic equation would look something like 6 plus minus square root of 6 squared, that's 36, minus 4 multiplied by 1 multiplied by 13 divided by 2a, and a here is 1 as well, so this is going to be 2, right? So our solutions to this, it's 3 plus minus 2 iota, because 13 multiplied by 4, 13 multiplied by 4 is 52, and 36 minus 52, that's a negative number, so that's why we get a complex solution, right? So since our roots are 3 plus minus 2i, our general solution should look something like y of t is e to the 3t c1 cosine of 2t plus c2 sine of 2t. Okay, so we have written a like general real solution when we found the roots, and now what we're gonna do is we're just gonna apply the general, like the initial value like the initial conditions given to us. So the initial conditions given to us are y of 0 is 1, right? So we'll just plug this in, and so y at 0 is equal to um, e to the power of 0, because 3 multiplied by 0 will be 0 itself, right? And then we have c1 cosine of 2 multiplied by 0, and that's again a 0, plus c2 sine of 2 multiplied by 0. And so that is equal to 1, right? And we know like cosine of 0 is 1, so that does exist, but sine of 0 is 0. So this entire term is just gone away. And anything raised, like a number raised to the power of 0 is 1. So what ends up happening is 1. And then we have c1 multiplied by 1 plus 0. And that's it. And this is equal to 1. So we know c1 is equal to 1, right? And now what we're going to do is we're going to differentiate this equation. So um, y prime of t should look like, okay, so I'm just going to differentiate the whole equation. And frankly, you can just use the multiplication or the product rule for this one, and it's pretty easy. So e raised to the power of 3t gets us 3 c1 c1 cosine of 2t plus c2 sine of 2t, right? And we're gonna have another term for this. So uh yeah, just a second. Yeah, this should have not been here. Okay. So if we differentiate the other part of the equation, so that gives us when we differentiate cos, that gives us negative sine, but that'll be negative 2c1 sine of 2t. And the other part is when we differentiate cos, that gives us, sorry, when we differentiate sine, that gives us a cosine. So that'll be plus 2c2 cosine of 2t, cosine of 2t. Okay. Okay. So we have an equation given to us here that we like differentiated, and then what we're gonna do is we're gonna plug the initial conditions in, and we can just find what the final answer is, right? So we know y prime of 0 is 1, and if we just plug this in is 1 equals e to the power of 0, that's just 3, c1, and we know cosine of 0 is still 1, and sine of 0 is 0, so we're not gonna consider that. So it's gonna be plus. So sine of 0 is obviously 0, so negative 2, and this is going to be multiplied by 0, and then we have um 2c2 cosine of 2t, but we know cosine of 0 is still 1, so we're gonna have 2c2 in this case, and that's it. So we have 1 3c1, 1 equals 3c1 plus 2c2, and what we found previously was c1 is equal to 1, right? So if we just plug in, so it's a one unknown one equation, we can just plug in the values and find out what c2 is, right? So 2c2 is 1 minus 3 multiplied by 1, so 2c2 is negative 2, c2 is negative 1. Okay, and from this, we already have our final answer for this question, which is y of t is equal to e to the power of 3t. Since our c1 was positive 1, we're just gonna, I'm just gonna write the value itself, which is cosine of, that's cosine of 2t minus, because this is c2 is negative 1, sine, that's sine of 2t. Okay, and this is our final answer for uh, I yeah, this is our final answer for the this is the real valued solution for the initial value problem. And let's jump to the other question. And okay, so it's like the ODE t squared y double prime plus 3t y prime plus y equals 0 has a solution y1 of t equals 1 over t for t greater than 0. And then we just have to find this general solution, right? So what's given to us is t squared y double prime plus 3t multiplied by y prime plus y equals 0, right? And this is a Cauchy-Euler equation, right? So the fastest method is to try a power solution of the form y equals t to the power of m, right? So if we substitute this into this, and then we just have to find what is y of prime. That's going to be y t m minus 1, and y double prime is m minus 1 t to the power m minus 2, right? If we plug these values in to the ODE, what we get is t squared m minus 1 um m minus 1 multiplied by t m minus 2 plus 3t multiplied by m t m minus 1 plus t to the power of m equals 0, right? And now we just simplify because it's m minus 1. So when you have, so what just happens here is we have a t squared multiplied by t to the power of m minus 2, right? So we just add the powers over here, the same happens on the other side. So this is 3m t1 plus m minus 1 plus t to the power of m. It's equal to 0. And this just gets, so 2 minus 2, that's 0, and then 1 minus 1, that's 0 again. So we have m minus 1 t to the power of m plus 3m t to the power of m plus t to the power of m equals 0, right? And we can just isolate the tm term, and that just gives us m squared minus m plus 3m plus 1 equals 0. And since tm is repeated all along, we can just just divide just divide both terms by tm. Over here, if we divide by tm, we just lose the tm, right? And that gives us m squared plus 2m plus 1. I think this is one of the quadratic equation forms that we've seen before as well. So we can just simplify this. And this is m plus 1, because a squared plus a plus b whole bracket squared is a squared plus b squared plus 2ab, right? This is just the general form of it. So from this, we know that m equals negative 1, right? And what we can do is, so this is a repeated root in a Cauchy-Euler equation, right? So the general solution for this would be y of t is c1 t of m plus c2 tm multiplied by ln of t. And if we plug the values of m in it, is what we get is c1 of t to the power negative 1 plus c2 t to the power of negative 1 multiplied by ln of t. And when we simplify this, what we end up getting is y of t is c1 plus c2 ln of t. We can just add them because their denominators are the same. There's a t negative 1, t to the power negative 1 in here. So since we were just given like one solution, y1 of t is 1 over t, like the second independent solution is ln of t divided by t. So our second independent solution for this uh, would be ln of t divided by t. So that's it for this one. Let's jump on to the next one. So this says we have to find a particular solution and a general solution of the ODE y double prime minus y prime minus 12y equals 3t multiplied by e to the power 2t. Right? So okay. First we'll find the characteristic equation. So this would be uh so okay, for the homogeneous equation, this gives us y double prime minus y prime minus 12y equals 0, right? So we'll do what we did last time, is we'll just replace y double prime by r squared. So that just makes it easier because we have a quadratic form and then we can just solve it pretty easily. So that's minus r minus 12y equals 0. So if we want to find the roots of this, we go through the whole process again. But in this case, I'm just gonna tell you what the roots are. So the roots for this are when we simplify this equation, we get r minus 4, r minus 3 equals 0. So r equals 4 and 3, right? So our homogeneous equation uh, changes to, what do you say, y of t is a mistake. Yeah, so this is c1 e to the power of 4t plus c2 um oh, I think I just made a little errors. This is r plus 3, which would give us negative 3 over here, and this gives us e to the power negative 3t. Yeah, ha, got that early. That's nice. Okay, so our homogeneous solution is basically this c1 multiplied by e to the power of 4t plus c2 multiplied by e to the power negative 3t. And since we have to find the particular solution as well for this one, what we're going to do is going to include the right hand side in this time as well. So the RHS that was given to us before, that was 3t e to the power of 2t, right? Okay. And if we're trying to find the particular solution to this, so our y of p in this case would be equal to e to the power of 2t at plus b. Okay, and we're just gonna take derivatives of this. So what's the derivative of this? Let's use product rule again, and we can just find that pretty easily. So this gives us e to the power of 2t a plus 2at plus 2b. And I'm just gonna move this so we have more space over here. Yep, that's perfect. Okay, and now we're gonna find the double derivative or the second derivative of the particular equation that we just solved. And what we end up getting for this one is e to the power of 2t, and this would be 2a plus 2a plus 4at, and then we would have plus 4b in this case. Okay, so if we simplify this, what we end up getting is 4a plus 4at plus 4b. Okay, so if we just plug all of these into our ODE, which was right here, our homogeneous equation, this what we end up getting is, this is going to be a long one, e to the power of 2t 4a plus 4at plus 4b minus e to the power of 2t a plus 2at plus 2b, and this is minus 12 e raised to the power of 2t a t plus b. Okay, awesome. So we have this. Now we just simplify. And if we simplify all of this, is we can just isolate all the e to the power of 2t variables, and then, or we can solve for each of them together, right? So if I'm just looking at terms including just the variable a, what we end up getting in this case is we have a 4a minus a over here, and that's minus. Okay, so yeah, 4a minus a. Yeah, that's it. And our a term is 3a. For b particularly, that's not so bad. So we have 4b minus 2b minus 12b. So what we end up getting is negative 10b. And if we're looking at the at term, that's 4at minus 2at minus 12e to the power. Yeah, oh, no, sorry. That's minus 12at as well. So this is negative 10at. And if writing our final equation, that is something that looks something like e to the power of 2t multiplied by 3a minus 10at minus 10b. Okay, so now we are going to compare this equation over here with our RHS, that was 3t e to the power 2t, right? So we just want e to the power of 2t with the coefficient 3t, right? This is our coefficient. This is what we want the RHS to be. So we're just going to compare this equation to the one that we just found. So that gives us 3a minus 10at minus 10b. And we can just cancel both these terms out because they're common in LHS and the RHS. And the only place where I see t is this term over here. So negative 10a is equal to 3. So a equals negative 3 by 10, right? And what we know is 3a minus 10b equals 0, because we don't have just terms that do not include the variable t, right? So we can only conclude that 3a minus 10b is equal to 0. So we have an equation given to us, and we can just plug this value in. So what this gives us what this tells me is 10b equals 3a, right? And we already found what a was. A was negative 3 over 10. And I can just find 3 over 10 multiplied by negative 3 over 10. That just gives me b is negative 9 over 100. So the particular solution to this problem, yeah, so the particular solution to this problem looks something like e to the power of 2t negative 3 over 10 t minus 9 over 100. Okay, so now we're going to write the general solution, that is going to be y of t is equal to c1 e to the power 4t plus c2 e to the power negative 3t plus our particular solution, that was e to the power 2t negative 3t over 10 minus 9 over 100. If you want, you could simplify this, but it's just how easier to write it this way, right? Okay, so this question we're done with. And right now, we're just gonna move to another question. And this question is asking us to solve for the position of a mass which is attached to a spring with no damping. If you can see, the no is particularly bolded, so that is important to remember. And no damping, if the mass m is 1 kg, the spring constant k is 4 newtons per meter, and x at 0 is those are just initial conditions given to us, and we have to write our answer in the form a cosine of omega t minus alpha. Okay, so for an undamped mass spring system, the equation is okay. So the equation for this one is m x double prime plus kx equals 0, right? And already what is given to us is mass is 1 kilogram, so I can just plug this in as 1, and anything multiplied by 1 is the number itself, and k is given 4 to us, so plus 4x equals 0. And we are going to find the characteristic equation for this one as well. So we can just substitute x double prime for r squared. So what we get is r squared plus 4 equals 0. So from this we know like r squared equals negative 2. So r is plus minus 2 iota in this case. So our general solution for this one is x of t looks something like c1 cosine of 2t plus c2 sine of 2t. And if you can look over here, there are initial values given to us, initial conditions that are given to us. So x at 0 is negative 3, and x prime at 0 is positive 6. So if I just plug this in, so x at 0, that's equal to negative 3. So cosine of 0, I think we just talked about this before as well. Cosine of 0 is 1. So that just gives us c1 plus sine of 0 is 0 itself. So it's c2 multiplied by 0. So we found that c1 equals negative 3. What I'm going to do next is I'm going to differentiate the equation. So I have another initial condition which says that x prime of 0 is 6. So if I just simplify the equation, what I end up getting is negative. If I differentiate the equation, what I end up getting is negative 2c1 cosine. Sorry. So the derivative of cosine is negative sine. So henceforth the negative sign. So that's negative 2c1 sine of 2t plus. Okay, so what's the derivative of sine? It's a cosine, right? And do not forget the chain rule. That's why we're writing the 2 in. So that's 2c2 cosine of 2t. And um, okay, that's okay. Oh, yeah, I just missed the negative sign over here. So this is the negative sign. So x prime at 0 is negative 6. We're just gonna plug this in. What we end up, sorry, that's a positive 6. Mhm. Okay, so that's a negative 2 c1 multiplied by 0, because sine of 0 is 0, right? Plus 2c2 cosine of 0 is a 1. So this is just going to be multiplied by 1. So we have 2c2, which is equal to 6. So our c2 is equal to 3. And our function is like, okay, so our position function is x of t is basically equal to 3 sorry, that's going to be a negative 3 because our C1 was negative 3. So it's negative 3 cosine of 3t. What was cosine of 2t? Cosine of 2t plus 3 sine of 2t. And that is our position function. But if you guys remember, we have to write our answer in the form a cosine of omega t minus alpha. So, right? So if we are to convert this into this form, is we just have to we just have to compare this equation to the form that's given to us. So I'm just going to copy the whole thing, and it's oh, that was not what I intended to do. So yeah. Okay, so this would be so we're just going to compare this equation to a cosine of omega t minus alpha. Okay, so so when we're comparing it to this one, it's basically we just have to change what form we are writing this in. So this is going to be equal to a cosine of 2t minus alpha equals a cosine of 2t multiplied by cosine of alpha plus sine of 2t multiplied by sine of alpha. Yep. And right now we just have to match our coefficients. So what we can do is we're just going to match the coefficients with the ones given to us over here. And that brings us to a cosine of alpha is equal to negative 3, and a sine of alpha is equal to positive 3. So what we can do is we can just square these values and add them, or because if you guys remember, a basic trigonometric formula is cosine squared of x plus sine squared of x gives us 1, right? So we're basically doing the same thing over here. And this basically brings us to a squared equals negative 3 whole bracket squared plus 3 squared, which is a squared equals 18, which is a equals square root of 18. And from this, we can just find, like, if we just plug the values of a in over here, we can just find that cosine of alpha is negative 1 over root 2, and sine of alpha is positive 1 over root 2. So if we remember our quadrants as well, I'm just going to do a bit of rough work over here. Is according to the quadrants, everything is positive, only sine is positive. That's tan and that's cosine. So since cosine is negative but sine is positive, that just brings me to the point that the angle alpha exists in the second quadrant, right? And that brings me to alpha is equal to 3 pi over 4. So our general solution, the way they wanted us to write, is square root of 18 multiplied by cosine of omega t, but we found that to be 2t minus 3 pi over 4. And that is our final answer for this one. And okay, so we're going over the next question, which states that a mass of zero point 0.5 kilograms stretches a spring 0.14 meters. So what I'm gonna do is I'm just gonna write what is given to us. So m is 0.5 kgs. It stretches a spring, so the displacement is 0.1 0.14 meters. And suppose the mass is displaced an additional 0.06 meters downward direction and then released with an initial upward velocity of 8 meter per second. The mass is in a medium that exerts a viscous resistance of 12 newtons when the mass has a velocity of 6 meters per second. So we basically have to write a initial value problem for the position x in meters at any time for acceleration due to gravity. Okay, so first what we'll do is we have to find the spring constant, right? And what's given to us is we're using g as 9.8. So if you guys have taken physics 1, you know f equals negative kx, and then we can use mg equals negative kx. But in this case, we won't be using negative because um yeah, it's written over here. It's supposed to be positive, right? In the positive downward direction. So it's just going to be kx, and that's 0.5 multiplied by 9.8 gives us k multiplied by 0.14. And then we can find the spring constant to be 35 newtons over meters, right? And now what we have to do is we have to find the damping coefficient, right? Because it's stated over there that the medium exerts 12 newtons of resistance when the velocity is 6 meters per second. So we can find the damping coefficient, which is equal to C equals 12 over 6, which is equal to 2 newtons second meter, right? And basically, so everything is given to us right now, and we can just write the differential equation because, okay, so according to the spring mass damper system is m, oh sorry, yeah, so m x double prime plus c of x prime plus c of x equals 0. And I think we found almost everything that we needed to find. So this gives us the mass was 0.5, so that's 0.5 x double prime. The damping coefficient was 2 x prime, and the spring constant was 35x. Okay. And we also have to write the initial conditions as well, right? So if you can see, it was written over here that the mass is displaced an additional 0.06 meters in the positive downward direction, right? So since the mass is displayed an additional 0.06 meters, so we can just conclude that our x of 0 is 0.06, right? And the other part that was given to us is it was released with an initial upward velocity of 8 meters per second. So x prime of 0 is equal to -8. Because why is it -8? It's -8 because it's upward, right? Where is it? Yeah, this is, an initial upward velocity, because these guys, they've decided that positive is downwards. So if it's upwards, that's going to be negative, right? So our final initial value problem for this one is supposed to be, so this this is a 0. Yeah. So it's basically 0.5x double prime plus 2x prime plus 35x equals 0. And if we read the question carefully, we can just find out what our initial value conditions are, right? Okay. And this is the last this is the last question that's given to us, right? And this basically asks us is we have to choose the best description of each system, like is it simple harmonic motion, is it overdamped, underdamped, critically damped, beating, resonant, or steady state pulse transient, right? So there are this is the key, and we have to look at two things. First, is the equation homogeneous or is it forced? So if the right hand is equal to 0, this is a free vibration system, so it's basically not forced. And if the right hand is not equal to 0, that means it's a forced vibration system, right? And the second thing that we look at is if it's a homogeneous equation, we have to classify by the characteristic equation, right? Okay. So I'm just gonna, if I can make this a bit. Okay. Yeah. Let's start writing from here. S- So two things to look at. First, equation homogeneous or forced. If it is, if it's homogeneous, RHS is equal to 0. If it's if it's forced, that basically means that our RHS is not equal to 0. And the second thing we look at, if homogeneous, if homogeneous, we have to find, we have to we have to basically classify by the characteristic equation or find the characteristic equation. So in this case, if it has two distinct real roots, that basically means that our system is overdamped, right? Overdamped. If it has repeated real roots, that's it has like x plus 1 whole bracket squared or something. So like it has repeated real roots, that means it's critically damped. Critically damped. Oh, okay. Sorry for the pause, but yeah. So as I was saying is if our, what do you say, if our homogeneous equation, um if our equation is a homogeneous equation, what we can do is when we find the characteristic equation and when we find basically the roots of the characteristic equation, we can uh, we can infer by the roots if our uh, equation is overdamped, critically damped, underdamped, or like simple harmonic, right? So if we have like two distinct and real roots, it's overdamped. Okay, if it's repeated real roots, that's critically damped. If it has complex roots, that basically means that the equation is underdamped. Okay. Um, and if it has no damping term and no forcing, no damping or forcing, that just means it is simple harmonic motion SHM. So I think let's go ahead with the first one, and this one. Okay, so two things to look at. So we just said if our homogeneous equations, if our equation RHS is equal to zero, it's homogeneous. So if it's homogeneous, what to do next? You have to find the characteristic equation, right? So like for A, that is x double prime plus 4x equals zero, right? So from this we can infer that this is a homogeneous equation, and uh now if it's a homogeneous equation, now we have to find the characteristic equation. So x double prime is r squared, so r squared plus 4 is equal to 0. So that basically gives us r equals plus minus 2 iota, which is a complex number, right? So since this is our characteristic equation gives us uh so since there is no damping or forcing, this is SHM. Okay. So let's look at the next one. It basically is 2x double prime plus 7x prime plus 3x equals 0. So from this we can find our characteristic equation to be 2r squared plus 7r plus 3. And what we can use here is we can just use the quadratic equation to find what the values of r here are. But in this case, I'm just gonna tell you what what the solutions for r are, and that's negative 1 over 2, and that's negative 3. So since both of our roots are distinct and real roots, our like homogeneous equation here is overdamped. Okay, so our equation is overdamped. Okay, so let's look at the next part, the next question. The next question, okay. So we can see that our RHS is not equal to zero, right? So this is basically forced, right? We can say that it's forced, right? So it says y double prime plus 1.8 squared y is equal to cosine of 2t. So since this is a forced, because our RHS is not equal to 0, right? Since our RHS is not equal to 0, what we get is our natural frequency. Our what we have to first find is our natural frequency. So our natural frequency is something that corresponds to uh oh, okay. Sorry, I think I copied the. Yeah, I was looking at the wrong question. Yes. Yeah. So our omega naught would be equal that be equal to 1.8, and our omega, this is our natural frequency, and and omega, this is equal to 2. This is our forcing frequency. So forcing frequency. So you can just see that these are close, but they're not equal, right? So since these are not equal, this is this is what we would call a beating equation. Um, let's look at the next one. I'm just gonna um write this one over here. And the next equation states that y double prime plus 4y equals cosine of 2t. So, okay. So y double prime plus 4y equals cosine of 2t. Again, we know that the equation is forced because our RHS is not equal to 0. And right now what we're going to do is find omega naught. So if you can see previously what we did is we have to like whenever we're finding the natural frequency we have to take the square root of the y value given to us. But since the value was already given in a squared form, we just took the original value that was 1.8. But for this one, when we have to find the natural frequency, what we have to do is we have to take the square root of 4. Okay, so what does the square root of 4 bring us? The square root of 4 is 2, and our forced frequency is also 2. Okay, so our forced frequency is also 2, right? So since the natural frequency and the forced frequency, they're both equal, that indicates that this is resonance. So I know this is a lot of learning, but I think with a couple of more practice questions, I think you'll just start remembering it. If it's forced and the natural frequency and the forcing frequency are not equal, the the equation given to us is a beating. Or if the natural frequency, forced frequency are the same, it's resonance, right? I'm just gonna continue from here. Okay. So this is E, and this is x double prime plus x prime plus x equals 0. And right now we know that the RHS is equal to 0. So this is a homogeneous equation, right? And right now what we're going to do is find the characteristic equation, that's r squared plus r plus 1 equals 0. Again, we use the quadratic equation to find the roots, or what we can do. So if we find the roots of this equation with the with the quadratic formula, x equals negative b plus minus square root of b squared minus 4ac divided by 2a. So that is our quadratic formula, right? What we end up getting when we solve this is r equals negative 1 over 2 plus minus square root of 3 over 2 iota. So since our what do you say since our characteristic equations roots are complex, right? This is a complex number. And if we try to find the discriminant, which is b squared minus 4ac, this is basically 1 minus 4, which is negative 3, right? So since our discriminant is also less than 0, this indicates that the equation given to us is underdamped. Okay, let's get on to the next one. So this one is y double prime plus y prime plus y equals cosine of t. Yep, that's it. So we know this is a forced equation, right? And so this is a forced equation because this is, since RHS is not equal to 0, forced equation. And there is a damping term in here as well, right? That's y prime. And the forcing term is obviously cosine of t. So the solution for this differential equation is it has a transient part that dies out because of the damping term, and it has a steady state part that remains. So whenever you come across this kind of equation where it is a forced equation and you have a damping term in as well, right? So this is the damping term. This is what we would classify as steady state plus transient. So this is SST. Okay, I think we're left with the last one, which is x double prime plus 2x prime plus x equals 0. So x double prime plus 2x plus 2x prime plus x equals 0, right? Since our RHS is equal to 0, we know that the equation is a homogeneous one, right? And right now what we got to do is we got to find the characteristic equation for this one. So it's r squared plus 2r plus 1 equals 0. We've seen this before as well. So it's r plus 1 squared equals 0, right? And these are repeated roots, right? So if you can see that the roots for this equation are just positive negative iota. So r equals plus minus iota, right? Um, oh, sorry. Uh, these are repeated real roots. These are not. This is not a complex number. Yeah. Sorry for a moment. It's -1, -1. It's the same thing again, right? So if you have real roots, real repeated roots, that means that our equation is critically damped. And I think this is also a very important part. So if you guys end up taking circuits one, this will be very useful as well because we actually covered this in circuits one as well. So it's a pretty fun thing to know. But I think that's all for now, and I hope you guys got a lot out of this from this review. So you guys have a good day and good luck with your exams. Take care.